Now we're good to go.
Okay. Okay. So you can't do anything. Okay. Now we're. So. Gleich.
Does it not extend?
Okay. So, okay, now I'm back in business here. Then I welcome you for the last subchapter of the mechanical systems, and the task which we had was elimination of the corrosive material. That's what we treated with the screens. The second was sand and fat. That is what we separated in the grid chamber. The third was sedimentable solids. That's what we did in the primary sorry, in the primary sedimentation tank. And now we come to the secondary sedimentation for separating the thickening and separating and thickening the activated sludge. Okay, we can do that more or less the same way we've done this before. We have again the criteria. Our water has still the same viscosity and the density of 1. The activated sludge, which we want to separate here, he has a density of, however, very close to the water, maybe 1,050 to 1,100. We do not know any diameter, and we do not know any form of the sludge flux, because and we know, the only thing we know is that they're not very shear resistant. So we have this sludge, and we can't even define nicely particles. So in this we are dependent on empirical research. What is a sludge sinking velocity? And the second thing is, we also need a thickening, because the sludge volume, when you look in an aeration tank, what you see is all brown. And when you wait for a second, you see that there will be some clear water parts or clear water, little, there will be little strands of clear water in the sludge form. And so you see, yes, the sludge can get to a higher density, and that gives us a little hope that you get a higher, that you get a solid concentration, because we have to separate, because we have to in our effluent, we have to have treated water, and out of our activated sludge tank comes a mixture of bacterial sludge and treated water. So we have to separate that, and we have to return the bacteria into the inflow of the system, and we have to get as much as possible effluent out of treated water. We have to, as effluent, so we can send that to the receiving water. So in a secondary clarifier, activated sludge has to separate from the wastewater in order to produce a supernatant effluent of treated wastewater, and the total suspended salts concentration with the total suspended salts concentration of less than 20 milligrams per liter. Well, 20 milligrams per liter is very, very conservative. With a good designed secondary clarifier, we are always below 5, no? And that's what we have to head for. In the US, it's only 30 even, but 30 is just not very good, to say very politely. And then we want to have a return sludge with a total suspended solids concentration that is at least twice the concentration of the activated sludge from the aeration tank, that concentration, which is the influent of the secondary clarifier. Because if you look at that, if you have the scheme of the figure number 1, we have here our wastewater line, oops, from the inflow to the effluent. We start with our screens, and we have our grid chamber, then we have our primary clarifier, and then we have these tanks, the aeration tanks. We have here our BioP, we have a denitrification, and then we have our aerator tank with a nitrification, then we have a recirculation, and then we have the element which is now of consideration, our secondary clarifier. So the inflow is what comes out of the aeration tank, and the effluent is our return sludge here. Well, is sludge, actually it's separated in 2 streams. We might do this right away. This is our surplus sludge, which leaves the system. In the surplus sludge are all the microorganisms which grow in the biological stage. This is all what we consider the mechanical treatment, which we have treated so far. And this is the biological treatment. Okay, in this stream, this is our return sludge that goes to the head of the biological system. This is our primary sludge. This is those 2 normally go then into the anaerobic digester. This is our sand, and this is our screen goods. The screen goods are not really good, but you have to treat them anyhow. Okay. Now we see here, we have this mixing point, and as I told you before, what process engineers, what they love, what they have to love, is balances. So we have a mixing point here, and we have a separation here. And now find clarify. So if you look at the balances, we also have a mass balance. The mass balance is, this is this is our Q, ZB, okay. ZB is from German, that means Zuflussbiology, also inflow biology. This is Q AN, which means affluent secondary clarifier. And this, at this point, it's Q ZK, that means inflow wastewater treatment plant. Now those volumes, because here you also have later a thickening, a pre-thickening, and the filtrates all go back into this stream here. So at the end of this, this is about, you know, anywhere, this is 100 liter per person and day as a PE, population equivalent. This is about, the screen goods is about 3 to 5 liters per year. So if you divide it by 300, you really don't need to consider it in comparison to the 100 liters per day, which is 36,000 liters per year, no? 36,500 liters per year. And if you deduce 3 or 4 liters, doesn't make any difference. This is the same here. This may be also 3 to 6 liters. And so on a daily basis, this hardly has any effluent. And what comes out after dewatering, because after the anaerobic digester, we dewater, and the solids that go out, it was 25% of solids. That's maybe, again, at this point here, it is 5 liters per PE a day, and at this point it is 1 liter per person and day, per person equivalent and day. Now, before we have a thick pre-thickening here, mechanical thickening, and then we reduce this to 1 liter, so 4 liters go back. And then those 2 liters go in here. They have a solids concentration of maybe 4 or 5%, and then we reduce that to 2%, and then we dewater it and we increase it to 25%. So we are, at the end of the day, we have something like 0.3 liters per day. So in the effluent, you will find here something which is equivalent maybe to 99.7 liters per person a day. So what we say is that QZK is close to QZB, and that is close to QAN. No? Normally, you're not allowed, and I criticize this, mass balance is not a volume balance. It's not a volume, no, a volumetric base. But as we talk here about wastewater and density is constant, we might as well, the mass balance is for constant density, it's the same as the volume balance. No? since we all talk about water here and water, and the density doesn't change anything, it even changes less than the volume, so it's within the mistake. Now we have, at this point, this is our QRS, return sludge. So we have that this is that of the secondary clarifier. And this is Q surplus sludge, no? Okay, secondly, we have component balance. What kind of components do we have? No, we have mechanical treatment. We're just talking about a continuous phase and a dispersed phase.
So you've got the solid material and you've got the suspended solids. I mean, that's
So we got water and suspended salts. That's all we have.
and
no?
that's it.
So we have just, the components are water. And total suspended solids, no? Because we're not interested in total solids, because the salt is in the water. We don't want to look at that, no? Well, how does that work?
I mean, as a microbiologist, I'd want to follow the carbon. I'd want to know, what the carbon balance for each component is and see if it sums.
Well, you have C, Ts of this stream. It's very simple. Times, no, plus C, TSRS times QRS plus, no, is equal Okay, why did I leave something open there?
I can't spot which term is missing.
Hmm?
Which term is missing? I can't spot it.
Well, it can be like well, what we don't consider is that you have a growth here.
So the biomass itself.
The biomass itself. So this actually comes in here, but it doesn't stay the same through this. So you got to really say something like this here. Give it a little bit term, because this is not the same concentration at this point as it is it at this point, because it includes. It's almost the same, but it's not exactly the same. No? This is close to 0, 5 milligrams per liter. Now this is actually also is equal, because this inflow, what we have here, this is also equal to QZK plus QRS BB, exactly. And therefore this is also equal to this one. Right? Because here at this we have our TSBB, which is our CTSBB, and we have also Q ZB plus QRS, no?
I love mass balance.
Good. Because you're going to see more of those.
I'll be back.
Okay. See you all and then later, no?
We even got a student on Zoom.
Okay. So, now, first of all, what can we find out? From our empirical experiments with the sedimentation of the secondary sludge, what we do is we take a cylinder. I hope this is not very, you didn't see this very good here, or is that clear to see what I draw here? Okay. You pour in 1 liter of activated sludge. And then you wait for 30 minutes. And you will find out this is sludge and this is supernatant. No? And this is the sludge volume. Well, this is what I mentioned before, but we really just need it here. And what you also do is from this from this same sample here, is you go on a filter, and then you retain the sludge here, and have the filtrate here. You wash this. And then you take this and dry it at 105, no? And what comes out is, and this is a TSS. In the sludge volume in milliliters, this is SV. And then you get the sludge volume index, which is SV divided by TSS. And this is actually in milliliters of sludge per gram of sludge. Total suspended solids, no? So this is a volume, this is, because when you, at this point here, you have the sludge all over suspended. And this is now a measure where you can take how much can I thicken the sludge and how much supernatant can I take out of the sludge. Okay, now I got to clean this a little bit away. Any questions to this here? Okay, this is, so I might clean this away here. How to determine the sludge volume index? Now at this point here, the TS, BS. BS is for bottom of the sludge tank. No? In this TSBS, as a concentration, this is equivalent to 1,000 divided by SVI, sludge volume index, times, I don't know, it's not the square root, it's cubic root? No, it's a root.
Ah, yeah,
Root of the time of thickening. This would be, in our experiment, it's a 30 minutes. But in a tank, you might have a longer time because you have here a zone for thickening and extraction. You have here a zone of density stream and storage. And you have here a separation and backstream zone. That's where the sedimentation takes place. This is where the thickening, where already the thickening, well, this is a little bit storage area because this is a little bit for when you get stormwater. So, because if you get stormwater, you have a higher hydraulic load, so more sludge from the aeration tank will flow over into the into the secondary clarifier. This is a zone that has something to do, mostly to do with hydraulic variances, and there we talk about stormwater. In stormwater, you have different conditions than in dry weather. And this is then the zone for thickening and extraction. Okay, so if we have determined our SVI, then this is by the measurement which we have to take, and standard values, no? That value for SVI is around 100 milliliter per gram. Now in TE, in a standard plant is 2 hours. It might vary from between 1 and 2 hours, no? But normally you take 2 hours. You just take less time if you do not have good denitrification. If you do have only nitrification, you cannot store the sludge so long in here because then you get an unwillingly denitrification, and then the sludge is going to floatate. Due to that, you have to solve that. No? Okay, then we have the sludge concentration. CTS RS, which is a return sludge. And that is a factor, scrape effector times CTS-BS. And the scrape effector is 0.7 for for the standard scraper, mechanical scraping, and it's 0.5 for this is for suction scrapers. The suction scraper is kind of like a Hoover, no? An aspirator, no? There you pump away the sludge from the floor, and this is of course where there's less sludge, the viscosity is lower, so you suck more of that thin sludge away, and then you finally suck water, and you have to suck more for sucking the thick sludge. Because when you have secondary clarifiers are mostly round, like shown here on the diagram. The inflow normally comes from above a pipe and is separated, and you have here a standard pipe or a shaft where the water enters, and then it's evenly distributed in the circumference. The level in here, because this is open, is of course the same level which you have open here, and actually this pipe goes up higher, and you have here normally a bridge, and in this bridge, if you have those scrapers like a broom, no, like a solid broom, then we talk about the 0.7, because a broom is pushing this to the center, where you take away the return sludge. But by moving the sludge around here, you get also a little bit dilution by the water from above. No? But when you suck it away, then of course you have the high, because most of the sludge, the fast sedimentating sludges accumulate here, and will thicken more, and so you have a high viscosity here. And so if you have the suction scrapers by the hoover, so you can hoover more and thin sludge from this side than the thick sludge here. And due to that, you have more dilution, unwanted dilution for technical reasons due to the scraping. No? I don't know a better word. I call them now broom scrapers. No? Maybe we have to look this up here. I can. I don't think I'll find this. I'll look it up in my technical dictionary. No. I can't take it. Oh, Zuckerman has that. There his word for. Yeah, suction scraper, they're really called. But it's only with C, no? And suction. You shouldn't put the K there. Sorry for that. This is actually what they're called. This is suction scrapers. And for these ones, for the other mechanical scrapers, I didn't find a better word. Okay. So now we know our. And now we want to know our CTS-BB. And this we can get out of this solid balance. This is So this is close to 0. This is close to QRS because, or as QSS is much smaller than QRS. And then this ends up that CTSBB is equal to is equal to QRS divided by Q sub B plus QRS times CTSRS. Okay, and the relation of QRS divided by QZB, that is what we call the return ratio. In German, Returnverhältnis, for that it's RV. So when we introduce that, then we have this is 1 divided by plus 1 times CTS RS. And since we have to dimension our secondary clarifier for the critical case, which is stormwater, then we have RS should not smaller or equal. Sorry. $75 for stormwater or for maximum inflow. So okay, now we can calculate TSBB in the function of 3 different parameters, or 4. It's SVI, it's TSTE, it's our F scraper, and it's our RS. And we have standard values which are recommended when you make a design for a final clarifier. This is what we can take out of the balances. Now, what more do we need to calculate? Well, we want to have the diameter of the tank. Also, we have learned that the superficial area is important. Well, basically, we have learned from our experiment how that we determined this by the residence time more than anything else. Because we took half an hour and then we measured the ESV, the sludge volume index. So it has something to do with residence time, but also we know from sedimentation criteria is the surface loading, as a hydraulic surface loading, and then obviously we need retention time in order to get the solids concentration, our return sludge. And there's also a bunch of empirical knowledge flown into this. I have done this. This is also in the text which I gave you. So let's first look a little bit back to the text after we clarified those balances. So we now know Mm. Well, maybe we have to do this a little bit with numbers. The result of this is when you go into, I should find Excel here. Oh shit. Just give me a second. I have to create something here. Maybe it works, maybe it doesn't work. Well, seems to work. No. No, unfortunately, I can't start here because I can't sign in, so I can't really open anything. I can't open it. So I have to do it on my computer, and I have just to give you the numbers when you calculate this here. So that's 12.6. For our standard values, oops, this is 12.6 grams per liter in TSS. Then times 0.7. That's 8.8. It's our return sludge. And now if I use 0.75, it's it's 5.03, no? So my TS PB is my TSRS. This is what our objective was. My CTSRS is measured to poof. Now, what I really want to show you is when we have here 100 liter per population equivalent, then we have here is equal to 75 liters per person equivalent in day. So we have at this point, we have 175 liters per person and per PE and day. Simpler than I thought. This is the inflow which we have here. And the effluent will be our 99.7, no? Or the 100 really, no? So the supernatant effluent is treated wastewater with almost all of the non-refractory pollution eliminated. We come later to that because we have the settleable matter and what is fine dispersed and in solution. This will be eliminated in the aeration tank by assimilation in the surplus sludge or in the activated sludge, or it will be eliminated by respiration and will be mineralized to water, CO2, and at the end, due to denitrification and everything, to nitrogen. This I'm going to show you when we treat the biological system, which is going to be another part. Here we just try to get this secondary clarifier controlled. So the pollutants are either degraded by microbiological respiration or are concentrated and removed with the primary or surplus sludge. With the return sludge, microorganisms and the refractory in the flux absorbed pollutions are returned into the biological reactors where they are mixed with wastewater. By the return sludge, the retention time of the wastewater, as the hydraulic retention time, and the retention time of the microorganisms, the salt retention times, in the biological reactor are decoupled. The decoupling of HRT as hydraulic retention time and SRT salt retention time was one of the most important inventions in biological wastewater treatment, and microbiological process engineering was really the base for that, and that has been really done in wastewater treatment for all fermentation processes and is still an interesting area of research. In activated sludge plant with nutrient removal, SRT is typically 10 to 30 times higher than HRT. This has to do because when we go into nutrient removal, the required time, and we're going to treat that extensively also and soon in the biological treatment, we need an SRT which is superior to the inverse of the growth rates of the slowest growing required microorganisms. And the slowest growing microorganisms in our system will be the Nitrobacter or Nitrosomonas, which do the oxidation of the nitrite to nitrate. They are the slowest growing microorganisms. They are the divas of our system. And they have an HRT it's of course temperature dependent, and at 10 degree or 12 degrees centigrade, they have a safety factor of 2 because you have different things that have a certain inhibition on the microorganisms because you have change in concentration and composition and all this kind of stuff. And then for keeping them stable, safe in the system, minimum SRT of 10 days is required. No? And HRT, as we will see later, in the aeration tank is about 16 hours, so it's basically half a day. You know? And if you talk about denitrification, because in denitrification where there's no dissolved oxygen available, the nitrifying bacteria cannot metabolize, so they just sleep, and so the required retention time is then expanded from 10 days to 15 days, because those 5 days you need for denitrification, and then in comparison to half a day of hydraulic retention time, you end up with about 30 times higher being the SRT than the HRT. Okay, sizing the secondary clarifier of the biological reactors for denitrification and nitrification are interrelated. Sizing the secondary clarifier, sizing because the biological reactor, the required size of biological reactor is dependent on this TSS concentration we can attain in the biological reactor, because the concentration of the total suspended salts in the reactor is a measure for the concentration of the microorganisms. And in order to get the to attain the required SRT, we need to have a sufficiently low food to microorganism ratio. But this is all what we're going to treat in biological systems, the FM ratio as a food to microorganism ratio. So, and if you have this, and the food, the amount of food is determined by the inflow. You have an inflow of wastewater and you have a concentration. So this is the amount of food as a kilograms of COD per day, which is the organic load to the biological system. Now, if you have a maximum allowable food to mass ratio, then you will have a required amount of microorganisms to need for totally metabolizing this food. If there's amount of food and you have a certain food to mass ratio, so we required a maximum food to mass ratio, and chances you have a minimum mass of microorganisms you need in order to eat all that food. Like if you have a mice eating a kilogram of cheese, maximum not more than a kilogram of cheese a day, and you want 5 kilograms of cheese eaten a day, then you need 5 mice, right, to eat it. And when the mice only eats half a kilo, then you need 10 mice. No? This is what I'm talking about. But we get back at that, and therefore, if I if I change any of those parameters, for example, if I have a lower, if I higher sludge volume index, if I have a worse, if the settling is not, because if the settling characteristics are not so good, I will have a higher sludge volume with the same total suspended solids. If this settability and thickening characteristics are not as good, then I will have a higher sludge volume for the same TSS. So, and if I have a higher number here, I get a lower number here. If I get a lower number here, I get a lower number here, and of course I get a lower number here. If I get a lower number here, I have less microorganisms, as a lower microorganism concentration in my reactors. So my reactors have to be bigger. This is the interdependence of or interrelation of the biological system and the secondary clarifier. Okay. The sizing of secondary clarifier and the return sludge ratio, flow of return sludge QSR, divided by inflow of the to the biological treatment, QZB, this is the RV, which you calculate, determine the TSS concentration in the biological reactor. This TSS concentration in the biological reactor is normally referred to in English literature as MLSS, mixed liquor suspended solids. So this is called the activated sludge. This is called our mixed liquor and suspended solids. That's equal to TSBB, no? CTSBB. And now another thing is, if I increase this ratio of my return sludge, then of course this is also going down, and I need a bigger reactor. Right? Or if I have a lower scraper, if I change from broom to suction scrapers, also I will have this number lower, I will have this number lower, and I need a bigger reactor. No? So these sludge volume index, the scraper is normally determined by the system, but sludge volume index and return sludge ratio, those are the two parameters that interrelate the clarifier sizing and the biological reactor sizing. Fine. A larger diameter and a larger depth of the secondary clarifier induces a higher MLSS. If settling and thickening properties of the activated sludge, the sludge volume index, and the return sludge ratio are constant. Well, I was just talking about if those things are not constant, but since those are the return sludge ratio, I can control by my pumps. No, I can because for this I have to use a pump here, and it's very easy, to change the flow through a pump. By a frequency inverter or something, I can change the frequency, I can change the rotation numbers, or I can control the flow of my return sludge pump, and so I have from the operation side, I have an influence on my RV. This I can just, by more or less, I have a maximum of what the capacity of my return sludge pumps are. There's a maximum I have, but I can lower it. And when I have pumps, normally today you have a frequency inverter, so you can lower the flow of the pumps. And then also an influence here is the diameter and the depth of the tank, because this was we talked about when I design a new plant, I want to find out what is the required diameter and what is the required height. This would be minimal, but of course, if I make it larger, my clarification, I will get a better thickening, because that influences this design, influences my retention time for the thickening here. Normally, it doesn't make any sense to make it much over 2 hours, because when I once reach those 12.6 grams concentration, the sludge volume is very high, and the sedimentation velocity and therefore the thickening decreases, of course, the more sludge I have, because when the sludge volume is very high, all the flocks stand upon each other, and there's hardly no sinking and no compression anymore, and reduction of the sludge volume. So normally it doesn't make any sense to make it much larger. This is only when you already have an existing secondary clarifier and you want to calculate the capacity of that. Then you can say, if I can overload it, and if I put on a higher hydraulic load, I'm conscious, I will not get my 5.3 grams of total solids in as MLSS. But then if I have sufficient volume in my bioreactors, then I can say, okay, I can make a compromise. I just need maybe 3.6. So then I can reduce my retention time, my 2 hours of thickening, and well, if I reduce this here to 1 hour, what happens? Then this is from 2 hours to 1 hour. That means this goes down from 12 to 10. No, it's very easy. 100 is 10, and triple square root from 1 is 1. No, then you go down to 10. So that's really not that, the influence is not that strong. That goes down from 10, this goes down to 7, and now you have to calculate 7 divided by 1.75. What's that? Yeah, it's 4. It's exactly 4. And this goes down to 4. No? Okay. Um, More volume of the secondary clarifier induces a higher MLSS for longer retention time in the thickening and evacuation zone, thus reducing the required volume of the biological reactors for denitrification and nitrification. For sizing the secondary clarifiers, imperial equations have been developed and have become part of the DWA design manual for activated sludge plants, which you find on the DWA A131. A major component of the imperial equation is the parameter sludge volume index, characterizing settling and thickening properties of the sludge. In secondary clarifiers, the sludge volume surface loading, QSV, is limited to 600 liters per square meter an hour, and for vertical flow, and to 500 liters per square meter an hour for horizontal flow, which is normally the case. Vertical flow, you just have in very small secondary clarifiers, just if you have maybe not more than 10 meters of diameter, which is about 175 square meters, but normally you build them up to 40 meters of diameter, and all those have, with more than 60 meters, have a purely horizontal flow, because it has to do with the depth. The depth of the tanks normally is not much more than 4 meters, because to going deep in the ground is very costly. And somewhere you're going to hit, because normally you construct your wastewater treatment plant close to a receiving water body. So if you go too deep, you're going to hit groundwater. And to make constructions in groundwater, you need to pump away the groundwater, and all this kind of stuff is very costly. So you try not to go too deep. No? So 5 to 6 meters is that mostly we try not to go deeper than that. No? And this sludge volume loading, that means that's liter of sludge. If we have 100 liters of wastewater, well, we have here 175 liters of aeration tank effluent, which is mixed liquor. We have 175 liters per person day, which we put into the mixed liquor. And now that means we have, this was per hour, so we have 175 liters per person and day, and we have a sludge volume. If we have an index of 100, here, sludge volume index, and if we have a TSS of 5, then we have 503 milliliters of sludge volume in 1 liter, 503 milliliters in 1 liter. So this times 175 times 0.503, that gives us roughly some 90 liters of sludge per person and day. No? 175 times 0.503. Well, it's 88 exactly liters of sludge per person and day. And divide that by 24. If we, well, normally we have to, for peak water, so we have to divide it by 16 or something, no? Because the clarifier has to work always. It has to work 24 hours a day, but you don't have 24 hours a day, you have an equal flow. So if you even work with equalization tank and everything, you will have some peak flow. And the peak flow is going to be higher. So what we say, the average of 24 hours, if you divide it instead of 24 by 16, that means you have about 50% over average is your peak flow. And if you want to limit a wastewater treatment plant to that, you have to have, it either needs to be, you either need to have a big sewer system and big plants. The quotient between peak flow and average flow is of course lower than for a small plant. Because in a small plant, all the people have breakfast at the same time, and everybody lives close to the wastewater treatment plant. So the water is rapidly there. In Munich, you know, the people that live close to the wastewater treatment plant, their breakfast comes, the wastewater from showering before the breakfast comes at the same time as the people that live farthest away that showered a day before. Because the water from the farthest point travels with 1 meter per second flow in the sewer system. It's so long, it's 90 kilometers, it travels almost for 24 hours. No? So, you know, you at the sewer treatment plant in Munich or any large city of that size, of a million more population, you will have the shower from a certain part of the people at every time. No? At 6 o'clock, 7 o'clock, 8 o'clock, 10 o'clock. At every hour you will have the wastewater from the morning shower of some people. At 6 o'clock, it's the nearby people that showered at 6 o'clock. 7 o'clock, you get the wastewater treatment plant of the people that live a little bit farther away, that their wastewater from showering at 6 o'clock gets to you at travels 1 hour. No? Then in a large city, also some people shower later, some earlier, so you get a pretty even inflow at the wastewater treatment plant. This is different in a small village. Because in a small village, there's no flow. It doesn't take longer than an hour from the farthest point. The wastewater gets to the wastewater plant. And in a small village, most of the people do the same thing at the same time. They always breakfast because kids have to go to school and whatever. So everything happens at the same time. So you get a peak in the morning, you get a peak at lunchtime, and you get a peak in the evening. No? And these peak rates in small villages have a factor of 3. And in larger towns have a factor of 1.5. No? So if we have 88 liters of sludge, and this is connected only hydraulically, then if we divide that by 16, no? Oh, sorry, I have to do this then. That means we have about 5.5 liters per person an hour on in peak times. So that means, we can connect, now if 500 we're allowed, and if you divide the 500 which we allowed in horizontal system by 5.5, we can connect 91 persons to 1 square meter of a clarifier, of a secondary clarifier. Okay, let me explain this again. There's numbers here. I can touch this away here. This is all we don't need anymore. This is the inflow of our secondary clarifier. Huh? And this is our surface area. We assume it to be 1 square meter, huh? To make it simple. Now we have an inflow of 175 liters per person equivalent a day. We have a sludge volume, that's Q Zn. That's the inflow to the secondary clarifier. And this is equal to Q ZB plus QRS. No? Then we have sludge volume of 503 milliliters sludge, no? Per liter. No? So this means we have a Q sludge of 88 liters per person equivalent in day, or equal to 5.5 liters per PE an hour peak, no? Okay, we allow it here 500 liters of sludge per square meter an hour. So out of those two, we can find out, just dividing this, we have 99 or 90, 91, 91, it's almost 91. It's a little bit less, it's 90.8 or something. This is our capacity. No? This is liter sludge here, no? So if you divide the 500, if you divide 500 by 5.5, you get 91, and the liter sludge cuts out, the hour cuts out, and you are left with square meters per PE. No? And when you now know the required surface area, you know how much PE you have connected to your treatment plant, because you know the inflow load and capacity from the inflow flow. That means because the 91 is also because we have 100 liters per day and PE. That means you have 9.1 cubic meter peak flow, no? Per square meter, no? Peak flow per hour per square meter, no? No, per day, pardon. Per day, no? Because I have the 91 PE, and every PE has 100 liters per person. 91 times 100 liters makes 9.1 cubic meter per day, and that's per square meter. So if I know now my peak flow, I can calculate my surface area, and if I know my surface area, and if I know my tank is round, I can calculate the required diameter, right? Okay, there's something, the only input you really need is you need this QSV. Huh? This comes from empirical knowledge. This is what you can deduce. This is just what you got to look up by the experience. Everything else you can calculate. The same thing was the four factors. What sludge volume index shall I use? What thickening time shall I use? What scraper factor shall I use? And what return sludge ratio shall I use? This is, data we have from experience. Well, the sludge volume index you just can't change. It depends on your wastewater. If you know. If you're calculating an existing plant, you can measure the sludge volume index, and you look at it, what it has been during the last 3 years, and then you take the highest factor, because with worst sludge volume index, the plant still shall work. And the scraper factor, because either you determine which scraper you're going to use, or there is a scraper, then you have to take the scraper factor for that scraper. And you can verify the scraper factor in an existing plant if you look at the ratio of the sludge. If you take a sludge sample from the bottom, when you just stop the scraper and leave it for an hour and take then a sample and take the sample in the return sludge, and then you can, because this relationship gives you the scraper factor. And the return sludge volume you can just control by your return sludge pump, no? And you know your inflow flow, so you can this ratio you can look what you normally operate, and it's in peak ratio you tried not to go over 75%, and in normal when you have just average flow you try to work with 100%, no? Not to have because then you just don't know, you don't need the full capacity. Okay, so we calculated the concentration, we calculated the required diameter, so what's with the depth? And also with the depth is okay, this is now here. No, so, you know what you will learn and find out is here. The parameters that determine the surface area and the depth of the secondary cleft are also interrelated. So, however, in a certain range, a loss of surface area shall reduce the required depth and vice versa. No? So I can just this is what I'm going to show you. In planning, the normal procedure in sizing a secondary clarifier is to assume the sludge volume index, considering the influence of the treatment objective and industrial wastewater influence on settling and thickening characteristics of the activated sludge. There we have a table that enlists it, and you see for nitrification, denitrification, which we look at, 100 to 150 is what you normally get, but it really is a little bit better than this table. At least to my experience, we have anywhere between 80 and 120. So 100 is a good average value, which we normally calculate with. And this is and for extended aeration that you get lower here, and we are somewhere in between, because nitrification, denitrification, we normally choose a longer than required solid retention time, because we have some reserve in our plant for an increase on load. Not because when we plan a plant, we have to have in mind that the plant is good for the next 25 years. So we've got to be a little bit careful and have install certain reserves. Can't be that if one more factory, a small, if one more bakery and a restaurant comes, I have to expand the treatment plant. Not the treatment plant has to be good for some reserves. And due to that, we normally are in between here. So in planning, the normal procedure in size secondary clarifier is to assume the sludge volume index in considering this influence. We have table 3 and list of typical values. The sludge volume index, the retention time, and the sludge thickening, and the evacuation zone, 1 to 2 hours, and the scraper factor. They determine the TSS concentration in the return and surplus sludge. This is what I showed to you. We right away have this. This is not correct here. Sorry, this is not the MLS. Oh, sorry, this is a mistake here, because this is a TSS in the return sludge. It's not yet the MLS. The MLS is when you make the MLS and the biological. This you have to correct, please. This is a CTSRS, no? And the MLS and biological reactor, the anaerobic tank for the biological reactor consists of those 3 tanks for BioP removal, for denitrification, nitrification, is determined by the TSSRS. This is what should be here, and the return sludge ratio, by the TSS balance, with the TSS of the inflow being neglected due to a considerable lower ratio of active anaerobic microorganisms TSS in comparison to the return sludge. First of all, TSZB is about, it might be 7, if it's high, it's 700, 70 grams per population equivalent a day, so that makes 700 milligrams per liter. And we have about 4,000 or 5,000 in TSBB, so it's, well, it's, you know, it's still more than 10%, but 40% of the 700 will be degraded, will be mineralized. So you have to take those off, no? And then you're with 400, then you're below 10% of the inflow. And so, you know, it's, we just neglect that. And then we calculate the MLSS, and this is a formula which we deduced, which I've deduced before, no? This is strange, because this is up here. Normally it was 0. I don't know what happened here. Something. Give me a chance to see this. Yes, change that. I don't know, the things I insert the drawings. Shit. Okay, now it's right here. Okay, I don't know why it's doing that. So this looks a little bit strange, because this 0 really means that this TSS of the influent is neglected in this case, no? So I put it to 0 here. So in the secondary clarifier, we have the 4 zones: the supernatant zone, the separation zone, the sludge buffering zone, and the sludge signet evacuation zone. The depths of these zones are calculated with the following empirical formulas, and the sum of the depths of all zones is the required depth of the clarification tank. You know, this is a sludge volume. This is our return sludge factor. You can calculate all those, and you will come up in a standard solution of something like 4 meters, or close to 4 meters, no? If I do that here quickly, it's 0.5 meters. H2 is equal to 0.5. Oh, yes. Well, I need to, QA is, the QA, which is in this formula here, is the surface loading, and that is our 9.1 cubic meter per day. So it's 9.1 divided by 24. That's it. That's 0.37. Is that right? Okay, that's a very low rate, however. Well, you know, it just is, you know, putting in the stuff in the formula here. The QA is actually is No, this would be just, because you have to put this times 1.75, because this QA just assumes for, it doesn't assume for the return sludge. Then it's probably by 1.5. Yeah, and then you're about one, close to 1, no? QA is 1 meter per hour. This is anywhere between 1 and, from my experience, between 1 and 1.6. That depends on what your return sludge ratio and all this kind of stuff is. Then we have times 1 times 1.75 and divide that by 0.497. So in our case, we get about 176 for H2. And so you just can keep calculating, and you'll end up altogether with about 4 meters. No? Let me look also at the time, because we just passed break a little bit, because we started at, we have now 3:30, no? No, before 2:30 we have. We started at 1, no? 2:30, yeah. So let's make us a break here, and I will calculate that, and then I'll come back at you. So we have a 10-minute break, no? Doing some homogenics here. So that's QA.
Da ist das unten rechts, da wo es kein Gallus gibt.
Ja, dies,
Innen.
this QA is, QA is, this is now, is because you have, as the effluent, you have those 100 liters per person, and you have 91 person. So you have, and their peak flow is 160 liters, because we had this factor of, 150 liters, no? Because of a factor of 1.5. So we have the flow, the effluent flow is 9.1 times the 91 times 0.15. That is cubic meter per hour, and that is per square meter. And that is 91 times 0.15. And that is, no, that's liters, and that we must, that's again, and that we got to divide by, it's actually 0.1 divided by 16, because we have cubic meters per hour. This is our peak flow.
Divided by 50.
There's something to do with the sludge loading, really applies to, jetzt müsste ich mal nachgucken, dieses Schramm. Das ist mir auch noch nie aufgefallen. Ich halte das jetzt auch für, was ist denn das jetzt? Das ist ein bisschen inkonsequent, befürchte ich. Nee, das ist... Das ist blöd, das ist nicht so gemacht, wie man es eigentlich hätte machen sollen. Der Fehler liegt hier drin, ich habe es gerade nochmal nachgeguckt, weil sie berechnen es anders. Also sie berechnen es eigentlich so, aber sie berechnen dieses QA, berechnen sie mit dieser Schlammladung. Und das beinhaltet ja eigentlich nur diese, also die Formel hier ist, sie berechnen das QA aus QSV durch SV. Das haben wir hier auch gemacht. Wir haben hier QZN genommen und haben das durch Liter gerechnet. Wenn du allerdings hier, sie nehmen praktisch die 500 durch die 500 durch die 503, also das sind Liter pro Kubikmeter. Nicht? Und dann bist du nachher bei knapp unter einem, dein QA ist knapp unter 1, diese 0,99, was sie auch ausgerechnet hat, was aber eigentlich nicht richtig logisch ist, weil wenn du das Schlammvolumen nimmst, dann nehmen sie nur den Schlammvolumenanteil, der aus dem Zulauf kommt und nicht der aus dem Return Sludge kommt. Weil sie sagen, aber irgendwie ist das Quark, weil das aus dem Return Sludge wird unten wieder abgezogen, aber es wird ja eigentlich alles unten abgezogen. Das ist so ein bisschen willkürlich gewählt. Ne? Das ist ein bisschen willkürlich gewählt. Ne? So, okay, it's 70:45. So what I did, what is different really in the norm is you should not use here the 175. You should here just use 100 liters because you should here use ZB. Since it's empirical equations, you got always to be very carefully what is a relation. So they don't take all the sludge because they consider that the return sludge that goes out here has not to be considered as a surface load. Then you end up here with a sludge volume with 50.3 liters per PA day. If you divide this by 24, you have 2 point something here liters, and then you end up here with something like a little bit less than 240 parts PE per square meter, and that gives you with 24 cubic meters per day, and that results to be a QA of about 1 meter per hour, or 1 cubic meter per square meter an hour. No? Okay, and if you enter that in the height and the different heights, that's when you will end up with the 4 meters. This is also commented here. In case of an evaluation of the existing secondary clarifier, the procedure is the same as in planning, but at the end, QSV is adapted for the calculated depths to meet the existing depths. This is how, because in most cases in Germany, older secondary clarifiers do not have a sufficient depth, so that you cannot just load them according to the full surface loading. Since you cannot change the depths, you have to live with what you got. No? With respect to feasibility, TSBB should be in the range of 3 to 5 kilograms per cubic meter. Assume an SVI in the range of 100 to 120 kilograms TSS, a sludge volume, surface loading of QSV of 500 liters per square meter an hour. The specific hydraulic surface loading results to be in the range of 0.83 to 1.67 meters. That depends on the TSS, no? And this depends also on the sludge volume index, and the other parameters, also the return sludge ratio. The hydraulic surface loading of the final clarifiers is thus, with this surface loading, considerably lower than the specific hydraulic surface loading of the primary sedimentation tank. And there we see that the settable matter, of course, has a better settling and thickening characteristic as our activated sludge. No? In designing secondary clarifier, it safeguards that the QSV safeguards the sedimentation of the sludge, and QSV and the depth of the secondary clarifier safeguard the mass flux and provide sufficient time for the sludge to thicken. This is how you dimension those. No? Okay, this is then, we have then finalized with the mechanical treatment stages and come to the biological reactors for elimination of pollutants by microbiological respiration and assimilation. In the biological treatment, pollutants are degraded, assimilated, or absorbed, or are eliminated by co-sedimentation with a secondary sludge. No, they are either degraded, which means they're by respiration, they are assimilated in cell growers, or absorbed, or you have also this in the secondary, in the biological reactors, you just not get purely in solution pollutants that are dissolved, but you also have pollutants which are not settable, but which are particulate. They are very fine particles that do not settle in the, you can eliminate it by filtration, there you'll find them, and you'll find them in the effluent of the primary settling tank. So in those particulates which do not settle, also because the density difference to the water is just really low. So you have those flocks that just floatate. You just don't get them settled, no? And we saw the difference that only 70% of the filterable particulate matter is eliminated in the primary clarifier. So it's 30% and just a biological system. And out of those 30%, only a certain fraction is biodegradable. And what's non-biodegradable, since you will not find them in the effluent where they are. So they have to be absorbed or because when you go in the final clarifier, you have all those flocks from the activated sludge. In those flocks, when they sedimentate, they make like a filter. So those flocks will just, co-sedimentate other flocks that are not maybe activated sludge, but which are just inert biological material that's not really biodegradable. No? And this is why I talk about this co-sedimentation. No? The pollutants in solution are degraded or assimilated by microbiological respiration. There's another way. They can't be, might be a little bit of absorption, but that's all. No? Nutrients are partly eliminated by absorption, by assimilation due to cell growth. Like ammonia and phosphates are not really, there's no way they can be absorbed or anything like that, no? Because they are very good. Like especially in the inflow, nitrogen is everything is in the form of ammonia, and ammonia is very good in solution. You just don't get it out, no? So it's 100%. And also the same is true for the all is something, a term you never should use in technology, because in the inflow of a wastewater treatment plant, like 70% of the nitrogen is ammonia. 30% is in form of proteins, mostly proteins, some nitrogen also in the DNA.
How much was it?
30.
30.
And out of these 30, because those proteins are almost exclusively in particulate matter, and from the particulates, 70% you get by sedimentation. So from those 30%, 70% makes 20%, 21%. They will be in the primary sludge. And 9% will be particulate in the filterable matter, which will, as a 9%, and will be in particulate in the inflow to the biological reactors. And of the 100% of the 11 grams per person and day of nitrogen in the inflow, as a 21% will be in the primary sludge, 9% is particulate in the inflow to the biological reactors, and 70% is in form of ammonia. Okay, in the case of phosphate, it's that 80% are orthophosphates, which you find when you take the inflow and you make a filtered sample. In the filtrate, you'll find 80%. So 20% is particulate, and from those 20%, again, 70% will be eliminated in the primary, and 9% will be, it's from 20, 70%, 14% will be in the primary sludge, and 6% will be in the particulate phosphate that will go into the bioreactor. Now from this 9 and 6%, 9% of the nitrogen and 6%, again, half of it is biodegradable. So it's only 4% that stays, so it's really neglectable. No? You can't really differentiate it too much, you know. So nutrients are, you know, partly eliminated by assimilation due to cell growth. Nicht? Ammonia and nitrogen in excess because it's in the cell growth. When you have cell growth, it's that 50%, roughly 50% of the COD is converted to cell mass, and 50% is mineralized in CO2, no? By respiration. And he has cell growth. From those 50%, due to the composition of microorganisms, the ratio that as a 2.5% of the COD that goes that's degraded, respirated, and assimilated as a 5%, roughly 5% of the assimilated COD is nitrogen. The nitrogen in the cells is 5% of the COD. That's assimilated in the cells. So the ratio of degraded COD, respirated and assimilated, to nitrogen eliminated by assimilation is 100 to 2.5. This is what we call the nutrient requirement. In order to grow cells, no, the yield coefficient of nitrogen into the cells is 2.5% of the COD, which is degraded, 50% mineralized, and 50% you will find also of the COD in the cells. And like if you take 100 grams COD, you will find that 50 grams of the COD you will find in the cell mass. In the cell mass, you have a COD to organic mass relation of 1.4. So the organic mass from the 100 grams of COD will be 50 divided by 1.6. So that's is equal to 50 divided 1.6. That meant, yeah, 9. Okay. Is 31.25 grams you will have in your hand as bacterial mass. And but this is only the organic part of it. And then 70% of the bacterial mass is organic, 30% is mineral mass. So the whole bacterial mass you will have is going to be 44.6 grams. No, you take 100 grams of COD. You will degrade them completely, and then you will have a cell growth of 44.6 grams of cell mass. 31.25 grams will be organic in that cell mass. And in that cell mass, you will have 2.5 grams of nitrogen, which you will have to add as a nutrient. No? If you just give COD, the microorganisms can't grow because they need nitrogen and phosphorus. And in this 44.6 grams cell mass, you will find 0.5 grams of phosphorus. So the nutrient requirement for degrading aerobically 100 grams of COD is, or the ratio is COD to N to P is 100 to 2.5 to 0.5. The ratio of COD to nitrogen to phosphate is 100 to 2.5 to 0.5. So if you want to degrade 100 grams of COD, you need 2.5 grams of nitrogen, which you will find in the organic mass, which will be grown, and you will find in this organic mass 0.5 grams of phosphor. No? Now, if we look at that in the numbers here, so let's clean this table here. Okay. If we just have a nitrifying, or if we just have a reactor for aerobic degradation, then we have here our microorganism, no? Our inoculum, and we have here our human being, and he produces wastewater. And that's 100 liters per day. That's 120 grams COD per day. That is 11 grams of nitrogen, total nitrogen per day. It's 1.8 grams of phosphorus per day. Now I did something wrong, so I have to make this, I missed because we have this primary. Then this goes into our primary sedimentation. And we get our primary sludge. No? And there we have in with here, this is 1 liter, and it is about 40 grams of COD per day, 1 liter per day. It's 1 gram of nitrogen per day, and it's 0.2 grams of phosphate per day. So in our biological reactor, and now we get our nice microorganisms here. We get here 99 liters per day. We get 80 grams COD per day. We get 10 grams of nitrogen per day. And we get 1.6 grams of phosphate per day, right? Okay, this goes in here. Now he converts to CO2, no? And with oxygen, he gets 40 grams of oxygen per day, and reduces the CO2. And then he produces surplus sludge. This is our surplus sludge. And this is here is the other 40 grams of COD per day. And now we have this ratio of 100 to 2.5 to 0.5. So in the COD we have, you have to divide it by 100. So it's 0.4, you multiply it by 2.5. So it's 1 gram of N per day. And it's 0.4 times 0.5 it's 0.2 grams of P per day, right? So in our effluent, we have, and this is a surplus sludge, no? And this we take out with 5 liters per day. But then we go into a filtration system. And we take out 1 liter per day in thickened surplus sludge, and the 4 liters go back as filtrate, no? And this is our surplus sludge thickened. Right. Then we have here 98 liters, no? Because 1 liter's gone here and 1 liter's gone here. Those 2 liters go into the digesters, and really those 2 liters almost come back completely as well, because after the digester we have another dewatering of the digested sludge. Dewatering of the digested sludge. And so this is again, so 90% of those 2 liters come back as a filtrate from the dewatering of the surplus sludge. So really, this is almost 100 liters, no? Because this goes into the sludge treatment, and from the sludge treatment we have another filtrate here, 2 liters or 1.8 liter filtrate from sludge treatment, no? And in this sludge treatment, there's even a certain, there's a little bit like 15% of nitrogen. So we have there's there's the load comes back from the sludge treatment, because 50% of the biomass, and this solids which we have in here, those 45 or almost 45 grams of biomass which we concentrated, and all the this out of this gram which we have here, if we digest those and make it to biogas, of course they release another 0.5 grams that come back here, no? So this is here, comes back 0.5 grams of N per day from the sludge treatment, if we have anaerobic sludge treatment, because half of this biomass we're going to degrade. No, and half of this as well, so it's really 1.0, no? This is from this one, and from this one here. 50%, no? Is released in sludge treatment, no? I'm a little bit surprised. It is so low, but it's... no, it's of the degraded. Sorry, this is wrong. This is the double. This is 2 grams. So this is 1.5 grams, really. Now it's right, and this is 0.4 grams, no? Because this is, again, this ratio, I told you, the 0.5 is from 100 grams, and we degrade 80 grams of COD. Only 40 grams end here, but the ratio, how they measured it, because it's a measured value, nicht, is the 2 grams of nitrogen, because it's 0.2 grams of nitrogen are assimilated for 100 grams of COD degraded. And since we degrade 80 grams, so it must be 2 grams that, that end up in this. So the concentration, because this 40 grams of biomass is again, if you divide 40 by 1.4, so this is this is here 28.4 grams OTS. Organic volatile volatile suspended solids, and total suspended solids is 40 grams. Comes a little bit low for okay, and this indicates times 7, this is about, this indicates then it's about 14 grams of proteins, no? And this is my surplus sludge, no? Okay, so about 50% of the organic matter is proteins, which is typically for biomass. Okay, then if we look at this, we have 11 or 10 minus 2 is 8 plus 1.5. So in the effluent we have 9.5 grams of COD. We have 0. In our effluent, we have 9.5 grams of total nitrogen. And from our phosphate, with 1.8, we have 1.6 minus 0.4, we have 1.2 grams of P per day. No? So we are fine with the COD, but we do have a problem with our nutrients. No? Hmm?
Nee, ich habe die, I have to dress you, yes, okay. 80, this is the composition of the sludge.
Where are you?
For the ratio from COD to nitrogen to phosphor.
This is effluent. And this all has to do with surplus sludge, no? This is surplus sludge. And this 50% is sludge treatment. This is the base of the calculation for these numbers here.
The composition of
This is a base for calculating these numbers here. No? This also has to do with here. Now we're on the topic which is of interest for you.
Oh, good.
Like we are in the aerobic degradation. This is what comes from the human. This is what is eliminated in the primary sludge. 1 liter, 40 grams of COD, 1 gram of N and 0.2 of P. That has to do with the sedimentation of the settleable matter. So what goes into the bioreactor is 80, 10, and 1.6. And now we look first at without nutrient removal. So we have our microorganism. He is consuming 40 grams of O2, 50-50, we just assume. It's not exactly 50-50. There's formulas for that to calculate that more explicitly. And the rest is going, the 40 grams COD will find assimilated. And when we have this nutrient requirement for and the COD ratio of biomass is about 1.4. So if you divide the 40 by 1.4, you end up with 28 grams of volatile suspended solids. If you assume 70% of ignition loss, you end up with 40 grams of total suspended solids in form of cell growth. And take the nitrogen out of this ratio, and assimilate is about 2 grams, is this ratio 2.5 to 0.5, maybe 2.5 to 3.5. Then you get this assimilation by 80 grams of degraded COD of 2 grams, nitrogen assimilated 0.4 grams of phosphate. And if you multiply that by 7, which is about ratio for nitrogen as TKN to proteins, then you end up with 14 grams, which is about 50% of the volatile suspended solids. No?
Okay. In terms of the composition of the volatile suspended solid fraction, what's the dominant flavored molecule? Carboxylic acids, presumably, are dominant. Is there anything
Where?
else?
We don't really care. You know, for us it's biomass. The only thing we don't really care what's in. We just know it's 14% of the proteins. We're not really caring about the proteins. We care about the nitrogen because we want to get it out of the water. What then happens is those two sludges go into the digester, and 50% is degraded, also of the proteins, and this is also protein, the 1 gram. So you have 3 grams, and half of it you get back, 1.5 grams. So you almost end up with no nitrogen elimination in normal bioreactor if you have no nutrient removal, and if you have just a primary settlement in a bioreactor only for carbon removal, and a sludge anaerobic digestion, then you get back all the stuff here, and because you end up with 11, and you end up with 9, so it's not really the big deal, no? And phosphate is a little bit better because phosphate is not, you almost don't get any phosphate out of the digester because most of it is captured in calcium phosphate precipitation somewhere. No?
If there wasn't if there wasn't precipitation of calcium as the calcium phosphate, what happens to the phosphate? I mean, do we know
Okay, then
those
out of these 0.6 grams, you would get 0.3 grams back here.
Okay.
Same thing.
What form would that be in, though? I mean, would it be free or inorganic phosphate, polyphosphate, bound organic phosphates? I mean,
No. This is because what comes back here is after, because in the what is those two, so those two areas, they go really. What happens in between here is this one. What happens in here between is digestion. And dewatering. The digest means 50% degradation of organic material, and that includes that really includes no, it doesn't include COD because most of the COD is eliminated in form of methane, but ammonia and phosphate, autophosphate come back. And because you have a dewatering, then the sludge goes away, and this is basically the filtrate. No?
okay.
So it's all dissolved, no? All in solution. Okay, now let's look a little bit what we have in here. So, in biological treatment, pollutants are degraded, assimilated, absorbed, or eliminated by co-sedimentation with a secondary sludge. Pollutants in solution are degraded or assimilated by microbiological respiration. Nutrients are partly eliminated by assimilation due to cell growth. Ammonia and nitrogen in excess of the demand for cell growth eliminated by nitrification of ammonia and denitrification of the nitrate, which is formed by the nitrification. Phosphor in excess of the demand of cell growth is eliminated by biological or chemical P elimination. Particulate pollution is partly degraded and assimilated, partly absorbed, and partly eliminated by co-sedimentation by inclusion in the sludge flocks. Okay, now I differentiated all those 3 different processes as a 13, 15, and 18, and you see there's gaps in between. That's because they explain a little bit more in detail the different degradation, because the degradation we talk first about is only the degradation of carbonous compounds. That's exactly what we see on the whiteboard. Show the microbial principles of the degradation, assimilation of organic biodegradable pollutants and nutrients. First, we treat of biodegradable pollutants, that's our COD and BOD, by aerobic degradation. Secondly, we look at nitrogen elimination by nitrification of ammonia and denitrification of nitrate. And third, we look to the elimination of phosphor due to luxury uptake as a result of resolution of polyphosphates in an anaerobic environment and a phosphor uptake in the following aerated tank for nitrification. Okay, first, elimination of biodegradable compounds by respiration. Okay, you see this here. This is basically what you see. You have the pollutants composed of C, H, O, N, and P. They all go into the bacteria, aerobic bacteria. The aerobic bacteria is taking up oxygen. It's giving up CO2. It's giving up water. This comes out of this section. 50% is of the COD is converted with oxygen to CO2 and water, and 50% is integrated into cell mass. Now, organic biodegradable pollutants are chiefly carbohydrates, proteins, and lipids. In nature, carbohydrates, proteins, and lipids are dominating organic compounds. These compounds make up more than 90% mass of the organic compounds of our food and the food of all animals, and thus more than 90% of the organic pollutants in wastewater. In wastewater treatment, these pollutants are measured as in form of COD and BOD. Nucleic acid, vitamins, enzymes are very important for life and metabolic pathways, but quantitatively their role is negligible. Monomers of carbohydrates are simple sugars like glucose, fructose, lactose, etc. Polymers of carbohydrates are starch, semicellulose, cellulose, and lignin. Molecular weight increases from starch to semicellulose to cellulose and to lignin, and biodegradability decreases in that order. All carbohydrates, however, have the same composition, as the sum formula of all carbohydrates is H2O and now times N. Now, the ratio of COD to organic mass of carbohydrates is 1.07 or 67. No? This is reaction of incineration, of complete oxidation of the carbohydrates. They just form CO2 and water, and there's you need 1 molecule of oxygen for 1 basic unit of carbohydrates, and that's 32 grams of oxygen for 30 grams of organic dry matter. The stoichiometric biogas potential of anaerobically degraded carbohydrates is 747 liters, normal liters, or liters at standard conditions. This is what the N is for, per kilograms of carbohydrates, with 50% volume of methane. I can't really use it. Okay. And the stoichiometric biogas potential of anaerobically degraded carbohydrates, well, we had that. So the calorific value of organic material can well be estimated by its biomethane potential as BMP. And we can consider 10 kilowatt hours per cubic meter of methane. And you can see 0.35 cubic meter of methane per kilogram of COD anaerobically degraded. Now, this is very simple because if you the COD of methane is 2 molecules of oxygen, because if you incinerate COH4, you get well, so this is 16 grams ODM, and this is 64 grams COD. So you have and this is 22.4 liters normal CH4. So if you divide those two, you get 0.35 liters normal of CO2 of CH4 per gram of COD. And that's 3.5 kilowatt hours per kilogram of COD. That's the calorific potential. No? The lipids are chiefly triglyceride ethers, fatty acids, which are saturated, are polysaturated with average chain lengths of 17 to 18. That's what you mostly have in fats you find in the environment. or then you will have a COD ODM ratio in the range of 2.7 to 2.9. It doesn't really vary too much. Theoretical biogas potential of the anaerobic degradation lipids is 1.44 normal liters biogas per kilogram of lipids, and you get a 71 volume percentage of methane. Then we just consider that no CO2 is captured in the water, no? Or by absorption, I think. Proteins have an average chemical formula of C17, H 112, O21, 0.5, and 20S. And so also the CDM ratio is 1.44, and theoretical biogas potential of the anaerobic degradation of proteins is 725 liters biogas per kilogram of protein with 70% volume of methane, considering that all the ammonia is absorbed in form of ammonia hydrocarbonate. Mass of proteins and biomass can be estimated by a rather constant ratio of protein mass to organic nitrogen by 6 to 7, basically. It's about 17%, so it's rather 6 and 7. This basic information on biochemistry can be very helpful in characterizing roughly the composition of an unknown biomass. If you get some waste, organic waste, there's rather simple analysis, because you just got to find out the COD ODM ratio. You got to find out the ignition loss, and then you got to find out the Kjeldahl nitrogen or the organic nitrogen, so you roughly know what proteins is, and then from the CDOM ratio you can roughly calculate what is carbohydrates and what's lipids. No? This is how this works here, and then you have this carbon. This is a carbon balance for the aerobic degradation, and this is a carbon balance for the anaerobic degradation. You see that half is respirated as a mineralized, and half of it goes into surplus sludge. And this huge amount of surplus sludge makes it easy to have enough biomass in your reactor, because from the converted biomass you can almost lose 5% in the effluent, and you still generate enough biomass to keep the system stable. This is different when you look at the anaerobic sludge, because 90 or 95% is in the biogas. That's where all the energy is. So those guys live of very little energy for themselves. They don't have energy sufficiently. And we know from composting that you even can heat up the mass considerably. And you can do always liquid composting and sludge. If you have 5% sludge, you will heat it up to 60 degrees centigrade easily if you rate it. Whereas you almost have no calorific change and degradation of anaerobic degradation of sewage sludge of the same concentration. And what else happens is that you have very low surplus sludge production. So to keep the anaerobic system stable, you really have to take care you don't lose too much anaerobic biomass. And this is also what you see here in the energy balance. This is in the form of ATP. ADP is about 30 kilojoules, so you produce here 12 kilojoules, which is 360 kilojoules out of the 87, which makes about 42% of efficiency for that ends up in the biomass, and some 58 or 57% end up in heat when you dissipate it into the fermentation. No? Whereas in anaerobic, you just get only 1/10 or even less, 1/20 of the ADP, but is when you take 2 moles of aerobic surplus sludge from the energy, if you look at it, you get 12 ATP, because only 50% is going to be degraded. and the others are in biomass. And here, if you take 2, you get about also 1.2 ATP, because out of the two molecules are almost completely degraded. So and this is why this relation is 1 to 10. No? Really, it's in the anaerobic, it's 5% here and 50% here. 1% is just too low. No? That you just, stoichiometrically, and from the energy, it doesn't make any sense. No? From the growth rate, it's 5%. Well, you might lose something in your effluent. So that's why this might be as high. No? Well, carbon and energy balance of aerobic and anaerobic metabolism. Aerobic metabolism is summarizing all chemical conservations of the substrates and cells in an aerobic environment. An aerobic environment is characterized by the presence of dissolved oxygen. Dissolved oxygen needs to be above 0. Aerobic metabolism is composed of catabolism, as all other metabolisms as well, which is an aerobic metabolism is the respiration or aerobic degradation, and the anabolism, cell growth or surplus sludge production. In biotechnologies, often want a cell growth. We, as wastewater engineers, we would produce to have less surplus sludge and rather have more respiration. No? In aerobic degradation, respiration, catabolism, the energy yield for the microorganism is 43% of reaction enthalpy, as comparatively high, allowing a high growth rates of the microorganism. Assimilation, metabolism. 57% of the reaction enthalpy is, however, set free in form of heat transfer into the medium. In domestic wastewater treatment, the wastewater shall only be warmed by less than 2 Kelvin, whereas in composting, temperatures of more than 60 degrees centigrade are attained in the compost. Okay, now for the students, how do you calculate that? Because if you look at the anaerobic degradation, you can calculate very fine how much methane you could get. And the aerobic degradation is nothing but anaerobic degradation and incineration of the methane. And then you got to exercise that. No? In aerobic metabolism, the ratio of metabolized COD to assimilate N and P in anabolism is 100 by 2.5 by 0.5. We did this exercise already. This is important for later N and P balances of the biological treatment. This is what you need in order to know how much you got to eliminate of the nitrogen or phosphate by nutrient removal. Okay, this is all in a short way because we made all the balances, so we really can calculate how much surplus sludge you get. You can calculate almost if you know it's 50% anaerobic degradation of the COD in the digesters, you can calculate your biogas, you can calculate the energy, you can make all the mass schemes complete those. No? Now it's just a matter of doing that. No? Elimination of ammonia and organic nitrogen. The organic nitrogen is, ammonia and organic nitrogen, the sum is often referred to TKN, total Kjeldahl nitrogen. That's due to the analysis was invented by Mr. Kjeldahl. And this is eliminated by nitrification, denitrification. Well, organic nitrogen is mostly in the form of proteins. A little bit is DNA in the side chain, but that's also negligible from the mass point of view. Okay, let's look at this. What happens, and we again have all those pollutants, HCNOPN, but really we are just talking about ammonia here. By deammonification, hydrolysis, and deammonification, that's wrong here. The ammonia is split off from the proteins, from the amino acids, really, because amino acids are the proteins are hydrolyzed into amino acids, and then by deammonification you get the ammonia. But most of the ammonia, anyways, is already in the inflow because from the urine, what's it called here, the Harnstoff, the urine, the urea. Urea is already hydrolyzed, and that happens in the sewer. No? But due to the high solubility of ammonia and water, it stays completely absorbed. No? You would need a pH of more than 10 in order to desorb the ammonia. Okay, then you give oxygen, and you have nitrosomonas for making the nitritation, which is the first step of the nitrification, and then you have nitrobacter to make the nitratation, and it's not anymore true because those were first identified to be the microorganisms to do the nitrification business, and long was thought that are the only ones, especially nitrobacter for that, but then they found by fish, fluorescence, in situ hybridization, they found a lot of other microorganisms also being capable of doing this nitritation and nitratation. These grow very slow, and they are not heterotrophs, they are autotrophs. Also they are chemolito-autotrophic microorganisms. That means they don't use, and the energy source is chemically, it comes from ammonia. The phototrophs are the guys who make the photosynthesis. They are lithotroph because they don't use an organic molecule, but they use an inorganic molecule, namely ammonia again, as an electron donator. And they are autotroph because they live on CO2 and not on organic for their growth, no? As a carbon source. Okay, then you have the denitrification, which is done by heterotrophic bacteria. Also, those guys are chemo-organic heterotrophs because they use organic material as for their for the energy source. They use heterotroph organic material for the growth, and they use again organic as a electron donator. So it's all organic stuff, no? The respiration. And these guys are the same guys that we used for degrading our COD. They just use then not dissolved oxygen, they just use oxygen from the nitrate. They are supposed to, and they do that in normal treatment plants, they do that they almost exclusively produce elementary nitrogen. What we do not want is that they produce dinitrogen oxide because it's clima-damaging gas with a factor of 240 in comparison to CO2, and methane we have also to take care of because methane has a factor of 24.
Is dinitrogen monoxide monitored?
Not really, but it has been surveyed in Switzerland from the EAVAC in different Switzerland plants, and they found out as long as nitrification runs well, you do not have almost no production of N2O.
Do we know what the source of N2O production is in these reactors? Because I mean, I've never heard of any organism producing N2O.
RAPS.
What was that?
RAPS. The yellow plant, oil plant.
The rapeseed plant.
Yeah.
Okay.
That's supposed to that's next to cars, or it's before cars, is the main source of N2O production. N2O, lachgas.
What is it about the plant? Do you know anything about why it is responsible for producing N2O? Just kind of odd.
But I heard that, and we have in Mecklenburg-Romania we have a strong, as we are rapeseed, is it?
Yeah.
Rapeseed. We are one of the very strong rapeseed producers, and I've heard that has considerable emissions for that.
Interesting.
And I've heard that, and this is in the Anamox process, there's also more, stronger, they can measure more N2O production. But I asked this in a conference actually because when I thought about this Anamox process for nitrogen removal from manure, and I'm still, whatever I do there, if I have nitrite, and it becomes a little bit touchy, because if you don't have a complete nitrification, then with the denitrifying processes you might run into N2O production. That's what I learned. This was what a guy from Vienna University once commented in a conference. This was a small conference in Boltenhagen, initiated by an electric equipment supplier. No? I think I should be able to research that. I think it was Dr. Novak from Vienna University claiming that. And they had done investigations. At that time, he said, we're not quite sure. We observed that. We're going to go more in detail. So then I heard this a little bit, and 2 years ago, I think, we had 19, that was before Corona, we had this the sludge process, and there was a how do you say, one paper dealing with the Anamox for for reducing the load from the nitrogen or ammonia load from sludge treatment to the plant. And there I asked, hey, what's about this N2O? I've heard from Vienna that they do see some problems there. And then the two ladies from Hannover University, for Bayer, and there was someone else. But they both said, yes, there is a certain production, but if you relate it to the load of nitrogen being eliminated, it's more or less the same ratio which you do have in a treatment plant. So it's stronger than if you have it in a treatment plant, but in a treatment plant we talk about concentrations of maybe less than 100 milligrams per liter, and here we talk about concentration of 2,000 milligrams per liter, and in that relation you have about by a factor of maybe 10, 15 more N2O form. But if you relate it to the kilogram of ammonia of ammonia nitrified and denitrified, it's a little bit less even. That's what they claimed, but that's more or less what they told us without having really paper on it. No? So that's still something. And if you do that in a big scale with manure, I think you have to investigate that thoroughly. No? So they don't build plants and later they close them all down because they have too much they blow out this N2O, no? Emission, not elimination. There are too much N2O emissions, no? That if that happens, it'd be a disaster.
Yeah. You said it was what, 25 more times potent than CO2?
200.
200.
250 some or something, which is a CO2 factor of N2O. It's one of the highest factors that you can have. No? Methane is about 20 to 25 I found in the literature, and this N2O is really very considerable. So, no. Okay, in nitrification, two different microorganism groups are involved. Microorganisms of both groups are cumulative autotroph. It means they use oxygen. Well, we had that. They use the oxidation of a chemical, ammonia, as a source of energy. They neither use organic compounds as electron donators nor as carbon source for the anabolism. So ammonia oxidized microorganisms, they are now called AOBs. That's pretty new. That started with the Anamox process that you differentiate them. They oxidate ammonia to nitrate, and nitrate oxidized microorganisms are called NOBs for nitrate. Oxidized nitrite to nitrate. In table 4 we have the reaction enthalpies of all these bacteria. We just might look at it right away. And what you see is the aerobic respirations was 112 is maximum what you can get. The nitration with 78 is not that much less, but it's the 75% of it, more or less, a little bit less. And the it's less than 70%. And then but the second step of the nitrification, the nitratation, is with 21 kilocalories per gram atom is by far less. So these are the most sensible microorganisms we have, the nitrobacter and whatever is of that kind. And again, of course, the denitrification, that's a 75% or a little bit more from the aerobic respiration, but the growth rate with the turnover with aerobic respiration and denitrification as a if it's dissolved oxygen as an oxygen resource, or if you have nitrate as an oxygen supply, that makes about 75% of the growth rate. So it's a 25% reduction.
I'm just, sorry, I think mostly in kilojoules. What's the ratio between kilocalories to kilojoules?
4.19. Because kilocalorie is this, when you heat up water by 1 degree centigrade. That's 1 kilo water heated by, and that's, you need 4.1 kilojoule to do that. No? CP of water. I just don't know what the gram atom is related to, no? What does that mean, really?
I don't know, it's actually one of the few times I've actually seen that written. That's one of the few times I've seen it written that way. Presumably presumably they're talking about the atomic mass of that particular atom, right?
Yeah, is it for one turnover, no?
Yeah.
Yeah, that's why. Okay, well, due to the low reaction enthalpy of the nitratation, the growth rates of NOB are low. Kinetic studies, however, revealed that NOB reached a maximum growth rate already at a very low substrate or food to mass ratio, as FM ratio, what means that the Ks value of the monokinetic is low. This Ks value is the FM ratio, where the bacterial growth rate mu is half of the maximum growth rate, mu max, which is a growth rate without any substrate or any other limitation. So non-inhibited. The Monod equation expresses the growth rate as a function of the SM ratio, and in German we do that with the S for substrate, but I think that's internationally anyways. So mu from the substrate concentration is mu max times S divided by S minus Ks. No, that's wrong, that's plus. Shit. Why did you change that? Sorry. Let me look here, I get obnoxious.
I always look this one up before I talk about it because
No, it needs to be plus. I don't even need to look it up because it's a definition there. I know I did that wrong. You look at it and you just don't see it. No? I actually can't change it here. This needs to be plus because if S is equal to Ks, mu S is half of mu max. So if S is Ks, you have Ks divided by 2Ks is half, and that's it. No? So it's a very simple thing, and it's kind of nice because if S becomes rather large, then it's much larger than Ks. So the this Boch is what's Boch? A fraction? Yeah, it's fraction. No? the fraction of s divided by s plus ks becomes close to 1, because then ks is very small in comparison to s. And if s is 0, then this fraction becomes 0. And of course, if you don't have any substrate, growth rate is 0. No? And so this is a very nice formula. And what is the interesting thing is here in this diagram, we have made the growth rate over the substrate concentration, and we have the substrate, the feeding rate, and the FM ratio actually. And if FM ratio is half of maximum growth rates, if you have half of if this Ks value is very small, then you have more or less this kind of a curve, and if it's larger, you have those kind of a curve. Heterotrophic bacteria are not all the same. The nitrificants are pretty well defined, and it's well known because from growth surveys by microbiologists that they at a rather low FM ratio already have very close to the maximum growth rates. And only by this is you can figure out that there is somewhere where the growth rates of the nitrificants is larger or is higher than the growth rates of the heterotrophs, is that you can hunger out the heterotrophs, and that the nitrifiers have a chance to have the same growth rates, because the substrate for the nitrifiers, of course, is less, because we have, if you look at it, you have in the aeration tank you have more COD than you have nitrogen, ammonia nitrogen. So there's more food for the heterotrophs, but you can lower the food for the nitrifiers to almost 0, and they still work at a full rate. No? So this is why you can get into this area. And so what you have to do is, when the nitrifying, you have to be in where the growth rates of the nitrifiers is higher than the growth rates of the heterotrophs. What then is going to happen, that nitrifiers are going to grow more than heterotrophs, and finally, because the FM ratio drops more and more, eventually you will have the same growth rates for both, because nitrifiers are going to grow as long, and if they get more and more, the FM ratio, because the mass is growing because they grow faster than the heterotrophs, and so they become more and more in the system, and finally they will be so much that the FM ratio will drop, and then you will get to a point where the growth rates of the nitrifiers and the heterotrophs is the same, and that'll be the stable point. No? And when you're here, it is that the heterotrophs will grow faster, and you will take out more and more nitrifiers. So the FM ratio of the nitrifiers will go higher and higher, but they will never grow as fast as the heterotrophs. And the heterotrophs is, since they are dominating, their growth rates will just decrease slightly, and will never decrease as much as to get into a stable nitrification. You can play that if you make yourself, if you start with that you have 10 nitrifiers and 10 heterotrophs, and when you have the growth rate of the one more than the other, then you're going to find out that because when they double both, you're going to have, if you start with 10 and 10, and both have the same growth rate, and then after one doubling time you have 20 and 20, and you take out half of them. No, because the number of microorganisms in the system is going to be constant. Because what you do is in your aerobic system, you will control you have a certain volume of your tanks, and you will control your concentration of the MLSS. Because you cannot allow that the MLSS is growing and growing by not taking out surplus sludge, because if you do that, you have a too high sludge volume load on your final clarifier. And so finally you will fill up, the clarifier cannot thicken all the sludge, and the sludge will build up in the final clarifier still until it just flows out of the final clarifier. So this is not what you want to get to. And if you play that, and if you now have less of the, if you have a smaller growth rate of the nitrifiers, so let's say only 5 grow when you have 10 growing of the heterotrophs. So you have after the first cycle you have 15 nitrifiers and 20 of the other ones. You take half of each out, so you will have 7.5 only of the nitrifiers, and you will have 10 of the heterotrophs. If this happens again, you're going to have 7.5 by half, so you will have 10. Take half of the 5. And if you just keep playing that on, you will find out that at the end of the day, you're not going to have any nitrifiers left in the system. And if you do it on the reverse side, it doesn't happen because then the nitrifiers at a certain point become more and more, and the FM ratio goes down, and this is where you get a stable, lower to the FM ratio of the heterotrophs. You can't wash them completely out. Whereas when the growth rate of the heterotrophs is bigger as they have more food, they will just not reduce their growth rate so much. Because the nitrifiers are less, they will just fill in the space of the nitrifiers. And you probably will not get, they will not have the load, because the nitrifiers, due to that, if the nitrifiers are expelled, it's hard. It hardly has any effect on the food to mass ratio of the heterotrophs. This is why it doesn't work the same way. If you would have, if you say that if the nitrifiers are reduced, that the heterotrophs will double and their F to M ratio will half, but that's not the case because they get always the same food. So they will not really reduce. This is not so significant as when because if they are here, they just can go this way and nothing is going to happen. Whereas these are going to stay probably somewhere here until and this is what we observe also in the real process. So we can discuss it to the evening if this is possible or not, but we know that this happens, that this is an area where the nitrification is unstable and will die away, because our nitrifiers will get lost. Good. So let's quit this because it's almost 4:15, so I think 8 hours enough for today. And we'll pick up here, and then we just don't have too much left here for tomorrow. So I think tomorrow, if we make we start from 9 to 12, we should be mostly done with what I have to present to you. So thank you very much for your attention, and then I wish you a nice evening, and see you tomorrow at 9. Good. Hmm. Okay, here's another. Kann gleich noch zu viel ausdrucken, ausdrucken. Hm? Was?
No, no estoy en el libro, no. El título no.
Hm. Mhm. Ja, kannst du ja machen. Kannst du mir schicken? Ich würde dann auch zusammenpacken hier gleich, ne? Wo ist denn Dings? Wo ist der hin? Barmers? Wo ist denn Sean hin, oder was?
Was hat der gefragt über Lachgas? Ob da in diesem Prozess auch Lachgas
Hm?
entsteht? Ja. Aber nicht so viel.
Ja, er hatte einmal gefragt, ob es überhaupt einen Naturprozess gibt, wo Lachgas entsteht. Und das war beim Raps, habe ich gehört. Jetzt ist es hier Barmers, Direct Life Science, Surplus Launch, Contains, Werber, Contains. Werber. Ich glaube, da noch was. Ist 5 Minuten noch oder sowas. Ach, Quatsch. Ein paar Minuten noch, dann habe ich es gleich. Komm, Klaus mal eben anrufen dann.
My son
found
broke
it.
his finger.
Hmm?
My son managed to break his finger. I had to go get him from the hospital.
Oh, shit. We finished now, no?
Yeah. See if I can stop the recording. Pardon me.
I corrected on the mistakes, since I've seen them.